Welcome to this explainer, where we're bringing you science simplified. You know, we basically live our entire lives assuming that things have permanence, right? That a highly predictable sequence of cause and effect governs our universe. But what if the very bedrock of our reality, down at the microscopic level of quantum entanglement, is entirely an illusion? Today, we're unpacking an absolutely historic milestone in physics, Einstein's quantum riddle solved. We're going to explore how a century of incredibly fierce debate has finally culminated in a discovery that completely shatters our understanding of the universe.
So we really have to start with the ultimate question here. Is reality an illusion? I mean, could something happening right here in front of you mysteriously and instantaneously affect something happening all the way over on the exact opposite side of the universe? This seemingly impossible question kicks off a century-long detective story into a phenomenon so bizarre, so completely counterintuitive, that the greatest minds in physics literally shouted at each other over breakfast trying to make sense of it.
Okay, let's dive into this. Section 1. The spooky quantum mystery, physics' greatest detective story.
Just think about the sheer contrast between our everyday common sense and fundamental reality. In our everyday world, if you drop a heavy glass on a tile floor, it shatters. Cause, then effect. That glass is always there, firmly rooted in reality, whether you're actively choosing to look at it or not. But down in the quantum world of atoms and subatomic particles, things are maddeningly fuzzy. Particles basically exist as mere waves of probabilities. In fact, quantum mechanics tells us that objects like electrons aren't even physically solid or definitively located in one spot until they are actively observed. It is literally like stepping into Alice in Wonderland, where the normal, comforting rules of physics just entirely melt away.
To truly grasp the incomprehensibly small scale of this quantum playground, consider this analogy. If you took a standard, everyday soccer ball and enlarged it so much that you could actually see its individual atoms, that soccer ball would have to be roughly the size of the entire planet Earth. Just let that sink in for a second. That is the unimaginably tiny microscopic scale we're talking about, where our standard rules of reality simply cease to apply.
And deep inside that tiny scale lives the prime suspect of our mystery, quantum entanglement. It's this powerful, almost magical connection between pairs of particles. When two particles become entangled, they influence each other instantaneously, completely ignoring the space between them. You could literally have one particle sitting right here on Earth and its entangled partner floating way out in the Andromeda galaxy. And whatever happens to one instantly, without any delay whatsoever, mirrors in the other.
If that's a bit hard to visualize, think of it like rolling a pair of rigged quantum dice. Imagine you put two of these dice into a cup, you shake it up, and you throw them across the table. They both land on a 6. Okay, you put them back in the cup, throw them again, and this time they both land on a 3. It's absolutely mind-boggling. You are watching two seemingly random processes, physically separated from each other, behaving in perfect, synchronized lockstep every single time.
Now, this synchronized behavior was so absurd, so entirely counter to the very fabric of space and time, that Albert Einstein completely rejected it. He fiercely protected the idea that nothing, absolutely nothing, could travel faster than the speed of light, so this instantaneous communication just had to be wrong. He famously dismissed entanglement as spooky action at a distance, and actually, this rejection sets the stage for our central historic conflict.
Which brings us to a clash of titans in Section 2. Einstein's quantum riddle, the century-long debate.
This century of debate unfolds beginning in 1927 at the famous Solvay conference in Brussels. Here, Einstein debated the brilliant Danish physicist Niels Bohr on a daily basis. Einstein would bring down a new, seemingly unsolvable thought experiment every morning at breakfast just to disprove quantum mechanics, and Bohr would frantically pace around all day until he finally solved it by dinner. Then, in 1935, Einstein, along with Podolsky and Rosen, published the famous EPR paper arguing that quantum theory was simply mathematically incomplete. They insisted particles were like hidden objects under cups, possessing definite properties just waiting to be revealed. Well, the debate sat entirely dormant for decades until 1964, when John Bell formulated a brilliant mathematical proof to test it. And finally, in the 1970s, John Clauser built the very first physical experiment in a Berkeley lab, literally using salvaged hand-me-down equipment to actually test who was right.
So, the absolutely crucial point here is understanding exactly what was at stake. We were trying to figure out which world we actually live in. Do we live in Einstein's world, A comforting reality grounded in common sense laws, a strict speed of light limit, where particles have hidden properties all along, much like a cleverly rigged magic trick? Or do we live in Bohr's world, an eerie, chaotic landscape of spooky connections across space, where particles remain in entirely undefined fuzzy states until the exact moment someone forces them into reality by measuring them?
To settle this debate once and for all, scientists realized a standard laboratory just wasn't big enough. They needed Section 3, the ultimate cosmic test, using the universe as a lab bench.
See, even after John Clauser's initial tests in the 70s showed that entanglement was likely real, a massive nagging question still remained. Was there a hidden loophole? Could some invisible unknown force, like a hidden common cause stemming from deep in the universe's past, have secretly rigged the experimental equipment before the test even started? To prove entanglement wasn't just a clever illusion, scientists needed an airtight way to guarantee true randomness.
And this leads us to the breathtaking cosmic bell test. A team of scientists traveled to a high-altitude observatory out in the remote Canary Islands. Instead of relying on a local computer to pick random settings for their experiment, they focused two massive telescopes on different incredibly distant quasars in deep space. They used the light from these quasars, light that had been traveling for 8 billion years, to randomly choose how to measure entangled photons right here on Earth. Just think about the poetry of that for a second. Because that ancient light started its journey long before the Earth even existed, there was absolutely zero chance that local physics or hidden variables could be secretly rigging the test.
After months of painstaking preparation and rigorously analyzing all that cosmic data, the verdict was finally in. Dominic Rauch, one of the leading scientists on the project, confirmed they found undeniable correlations. Bohr was right. Einstein's alternative explanation of hidden properties was conclusively shoved into an impossibly tiny, implausible corner of the cosmos. Spooky action at a distance is undeniably 100% real.
And this brilliantly illustrates why solving this riddle isn't just an abstract academic exercise. Let's move to Section 4, the quantum tech revolution and why spooky action matters.
To understand how this completely changes our future, let's contrast standard computers with quantum computers. Standard computers use standard bits. Think of a bit as a light switch. It is strictly set to either a 0 or a 1, off or on, calculating tasks sequentially, laboriously taking one step at a time. But a quantum computer? It uses qubits. Thanks to the fluid, fuzzy nature of quantum mechanics, a qubit can be a 0, a 1, or an incredibly complex fluid combination of both at the exact same time. By entangling these qubits, a quantum computer leaps from sequential processing to exponential processing, literally mapping out millions of possible solutions simultaneously.
Take the number 72, for instance. That is the number of entangled quantum qubits in a specialized array chip developed at Google's Quantum Computing Laboratory. This microscopic quantum playground holds staggering, almost terrifying potential. On one hand, it can optimize global logistics and solve massive medical problems in seconds that would take normal computers hundreds of years to figure out. But on the other hand, it possesses enough raw processing power to instantly crack the modern encryption algorithms that currently protect our entire global digital economy.
Knowing this massive security threat is on the horizon, researchers are already acting. In China, a team led by Jianwei Pan actually built a secure fiber optic network spanning over 1,000 miles from Beijing to Shanghai just to protect data using quantum encryption. But there's a physical limitation here. Optical fibers inherently degrade the signal over long distances. So even a 1,000-mile stretch wasn't enough to build a truly global, unhackable network. To overcome this terrestrial hurdle, they had to look up to the stars.
The result is the blueprint for an unhackable quantum internet. By launching a specialized satellite into orbit, researchers can beam entangled photons directly through the vacuum of space down to different receiving stations on Earth. And here is exactly why it's unhackable. If an eavesdropper so much as tries to intercept the signal, the very act of them measuring that photon forces it out of its fuzzy state and instantly breaks the entanglement. The intrusion is immediately detected by the users. This means your data is safeguarded not just by clever software, but by the fundamental laws of physics themselves.
Let's move to and see how this builds into our final point. Section 5. Rethinking reality itself. The holographic universe.
If we truly accept that entanglement is real, that particles genuinely communicate instantaneously regardless of the distance between them, we really have to confront what that means for space itself. Researchers are now exploring a highly radical theory. What if space and time aren't actually fundamental? Think about temperature for a second.
When you feel heat, you aren't feeling a temperature particle. There is literally no such thing. Temperature is simply an emergent property. It emerges from the rapid movement of atoms. In the exact same way, the three-dimensional space and time we experience every single day might simply emerge from vast networks of entangled quantum particles existing on a distant, two-dimensional spherical screen.
This profound idea beautifully resolves Einstein's initial paradox. As researchers point out, if space itself is actually an illusion created by quantum bits on a distant screen, much like a massive holographic projector, then two entangled particles aren't really communicating across huge empty distances faster than light at all, because fundamentally, there is no space anymore. They are right next to each other in the underlying code of the universe. Which leaves us with a deeply provocative thought to end on. A century ago, Albert Einstein looked at the quantum world and told us it was simply too spooky to be true. But by proving him wrong, we didn't just break the rules of classical physics, we may have unraveled the very concept of reality itself. If space as we know it doesn't actually exist, what is the true fabric of our universe? And what else are we experiencing every single day that is nothing more than a magnificent quantum illusion? Thank you for watching this explainer, and stay curious.